Good morning, children. Good morning, all. Warm welcome to another chemistry class. In this session, we are discussing some important questions from the chapter Hydrogen. Chapter 9, Hydrogen. Let's see some beautiful questions from that chapter. Yes. Can we start? Ready? Yes. See the first question. The order of ionic character. That is the point. Order of ionic character of hydrides. What given is group 2 hydrides. See whether group 2 hydride or group 1 hydride, the ionic character will be increasing down the group as the electropositive nature of metal increases. As all of you know, whether group 1 or group 2, down the group, metallic character increases. So correspondingly, the ionic nature of the compounds will increase. So hydrides also, as the metallic character increases, the electropositive character increases down the group, the ionic character increases. I am sure you remember beryllium hydride is learned in the chapter showing covalent character. Beryllium hydride, magnesium hydride, they are polymerizing. It is referred in the NCERT. So they are more covalent in nature. Beryllium hydride is more covalent in nature, and down the group ionic character will increase, and the answer is which one? Option 3. It is beryllium, calcium, barium. Beryllium, calcium, barium. Like that. Okay? Second question. Third choice. The method used to remove temporary hardness of water is. Method used to remove temporary hardness of water. Temporary hardness of water removed by boiling process, removed by Clark's method. Might have learnt. While the other methods, ion exchange method, Calgon process called a permutator process, Calgon process using sodium polymetaphosphate. Then synthetic resin method, organic synthetic resin method. Then ion exchange method, that is permutate process, right? Using silicates, zeolites, etc. So the answer here is no doubt first choice itself. Clark's method, by adding calculated amount of lime, we can remove the temporary hardness. And I am sure you remember the reactions concerned. By adding calculated amount of lime, you can precipitate calcium as calcium carbonate, magnesium as magnesium hydroxide, etc. Right? Third question. Thermal stability order. Thermal stability order. It is referring to hydride's thermal stability. You see, this is a general aspect. Thermal stability decreases down the group. Thermal stability decreases down the group. Acidic character increases down the group. Bond angle decreases down the group. Reducing property increases down the group. Stability decreases down the group. So down the group for hydrides, thermal stability decreases. That is a fundamental idea. So which is most stable? It is referring to oxygen family. It is referring to hydride of oxygen family, and no doubt the most stable water molecule. So it is oxygen, sulfur, selenium, tellurium, polonium. Second choice is the correct answer. Most stable is H2O, and down the group the thermal stability decreases. Bond dissociation enthalpy decreases. Dissociation constant increases. Ka value increases. pKa value decreases. Bond angle decreases. Reducing property increases. So these are important points connecting to the the trend of property concerned to the hydrides. You need to remember. The answer is no doubt second choice. അടുത്ത ചോദ്യം. Match the following. Match the following. Carbon monoxide hydrogen, that is called a synthesis gas. A with 3. A with 3. So third choice out. Temporary hardness. Temporary hardness caused by 1. Magnesium, calcium, bicarbonates. So 3 and 1 will take you to the answer. So these are out. Second choice will be first one. So A3, B1. What about C? C2 correct or not? C2, diborane, an electron deficient hydride. An electron deficient hydride. I think that's a misprinted word. An electron deficient hydride. C with the 2. What about D? D with the 4, correct or not? Hydrogen peroxide, non-planar structure. You know, hydrogen peroxide is maintaining somewhat like an open book structure. It is a non-planar structure, known to all. Right? So, fourth choice is the correct answer. Next. In acid medium, H2O2 reduces MnO4 minus 2. You see, in acid medium, MnO4 minus is converted to what? In acid medium, permanganate will be switching to Mn2 plus. In acid medium, permanganate will be switching to Mn2 plus. So this is reduced while this is oxidized. H2O2 upon oxidation, you will get oxygen. Right? Oxygen minus 1. Oxygen minus 1 oxidized to 0. Suppose H2O2 undergo reduction, what is happening? You see, H2O2 undergo reduction, it will be converted to H2O, where minus 1 switching to minus 2. While H2O2 undergoing oxidation, you will get oxygen, minus will convert it to 0. So H2O2 can undergo oxidation as well as reduction. Is a good oxidizing agent and a mild reducing agent. Right? So here, MnO4 minus is reduced to Mn2 plus in acid medium, while H2O2 oxidized to oxygen. That is the reaction. Okay? Next question. Terrestrial hydrogen contain protium, deuterium, tritium. The approximate number of tritium atom in a sample of hydrogen that contain 1 mole protium. See, regarding the availability, the abundance of these isotopes, there are clear specification and statements given in the textbook. For protium versus tritium, how much is the relative quantity? Referred in the textbook, I'm sure you might have read about. There is 1 tritium associated with the 10 power 18 atoms of protium. It is commented in the textbook. It is commented in the textbook, I am sure you might have read. There is 1 tritium associated with the 10 power 18 atoms of protium. Now what is our question? For 1 mole protium, how much it is? For 1 mole protium, how much it is? So for this much of protium, it is 1 tritium. So for 1 protium, it is 1 by 10 power 18. And for 1 mole protium, it will be into Avogadro number. Very simple. For this much of protium, there is 1 tritium. Therefore, for 1 protium, it will be 1 by 10 power 18 tritium. And for 1 mole protium, into Avogadro number. And this is the answer. Avogadro number divided by 10 power 18. You will get this much of atoms of tritium. And the answer will be option D. Option D. So this question is based on 1 sentence commented in the textbook. And there will be questions like that. That's why we insist on line by line of NCERT. Line by line of NCERT is important. And you have to read between the lines also. Okay, next question. Anhydrous barium peroxide is not used with sulphuric acid in order to prepare H2O2 because why we are using for the preparation of hydrogen peroxide, we are using barium peroxide. And you know, we are using hydrated barium peroxide. Hydrated barium peroxide is essentially required. Now the question, why? Why so? Why? Because option D, barium sulfate will form a protective coating over barium peroxide, thereby preventing further reaction. Initially, there will be reaction. This will be interacting with this, and you will get hydrogen peroxide and barium sulfate. And you know, barium sulfate will make a coating over barium peroxide, and that will hinder the reaction. And suppose if it is hydrated barium peroxide, there is water in it, and the reaction will sustain. That is the point. That is the point. So if it is hydrated barium peroxide, there is water content within the substance and it can sustain the reaction. Otherwise, what will happen? The barium sulfate formed over the surface of barium peroxide due to initial reaction will hinder the further reaction. That's why we insist on hydrated barium peroxide. Okay? Next question. The percentage of 50 volume H2O2. All of you remember 100 volume H2O2 marketed as 30%. Therefore 50 volume will be 15%. 15%. Right? Yeah. Percentage by weight is 3.3 volume. Percentage by weight is, weight by volume percentage is 3.3 volume. Why? How it is that? Just now I told 30% equal to 100 volume. Therefore, 1% will be 100 by 30. That is 3.3 volume. I am sure you remember the strength of hydrogen peroxide expressed in terms of volume strength. Please learn that area. It's very important. Volume strength. What is volume strength? What is meaning 100 volume hydrogen peroxide? It means that, what is the meaning? It is the volume of oxygen liberated at STP by 1 volume of H2O2 sample. When 1 ml H2O2 decomposes, 100 ml oxygen liberated at STP. And that's how it is called a 100 volume. 50 volume means when 1 ml decomposes, you get 50 ml oxygen at STP. 20 volume means when 1 ml H2O2 decomposes, you are getting 20 ml oxygen liberated at STP. Right? That is the volume strength. And volume strength related to percentage strength and is nothing but is directly referred in the textbook. 100 volume marketed as 30% or 30% marketed as 100 volume. Next. When two ice cubes are pressed together, they form a single piece. The forces involving are, what is the doubt in it? Hydrogen bonding. In water molecule, in ice, the structural entity contained or the characteristics are decided by hydrogen bonding. Hydrogen bonding is the most important intermolecular forces involving in water molecule. All of you know. It is hydrogen bonding. Next. Lead dissolves more in soft water than in hard water. Lead is soluble in soft water. It is particularly called plumbo solvency. Once we were using lead pipes for water supply. And that has been removed because of this Plumbo solvency. Lead gradually can dissolve in soft water. And it being a heavy metal, it is creating problems. It is not good for the body. When it is small amount contaminated in the drinking water, it will be depositing in the, it will create so many problems in the body, all of you know. And that phenomenon, it is referred to as Plumbo solvency. What is the answer? Lead dissolves more in soft water than in hard water. Option D. In hard water, you know what happens? It forms the insoluble chloride and sulfate of lead, which forms a coating over lead that decreases Plumbo solvency. In hard water, the Plumbo solvency, the dissolution of lead is low because of the presence of chlorides and sulfate. It forms lead chloride, which forms a coating. It forms lead sulfate, which forms a coating, and that prevents any further dissolution, which is not happening in soft water. That is the point. Number of moles of H2O present in 1 liter water, sometimes referred to as molarity, is number of moles of H2O present in 1 liter water. Number of moles is equal to mass by molar mass. 1 liter water means 1000 ml. 1000 ml is 1000 gram. So it is 1000 gram divided by molar mass, which is 55.5 mole per liter. Option D. In so many numerical calculations, you might have seen that data. It is sometimes referred to as molarity of pure water. It is nothing but 1 liter water, that is 1000 ml. 1000 ml is equal to 1000 gram because density of water is 1 gram per ml. 1000 gram, 1000 ml. 1000 ml, 1000 gram. So number of moles will be 1000 divided by 18, 55.5. Next. The degree of hardness of water is expressed in terms of amount of calcium carbonate. See, hardness is caused by the salts of calcium and magnesium like bicarbonate, chloride, sulfate. So calcium chloride, calcium sulfate, magnesium chloride, magnesium sulfate, bicarbonates, these are all causing hardness. But the relative hardness of water is referred in a unique standard. All these quantity can be related to the equivalent quantity of calcium carbonate. Suppose you are finding the quantity of magnesium sulfate, you equate that quantity with the calcium carbonate. So equivalent amount of calcium carbonate is the reference standard for measuring or expressing the degree of hardness. So degree of hardness is always expressed in terms of calcium carbonate. If you are having 1 mole magnesium sulfate, it is equivalent to 1 mole calcium carbonate, and thereby you can express the degree of hardness. And if you are referring to 1 mole calcium chloride, it can be equated to 1 mole calcium carbonate. So always the reference standard is in terms of calcium carbonate. Okay, because otherwise the references will change because hardness causing materials are different. All are taken into one particular reference substance, that is calcium carbonate. Next, the degree of hardness of hard water expressed in terms of amount of calcium carbonate. The total hardness is expressed in terms of calcium carbonate equivalent to total amount of calcium and magnesium ions present per liter of hard water. Next. When the same mass of zinc is separately treated with the excess of dilute sulphuric acid and NaOH solution, the ratio of volumes of hydrogen evolved is, see, 1 mole zinc can produce 1 mole hydrogen. 1 mole zinc is divalent. 1 mole zinc can produce 1 mole hydrogen, whether in acid medium or in alkaline medium. It will give you 1 mole zinc, 1 mole hydrogen. Whether in acid medium or in alkaline medium, So what is the answer? 1:1. The answer will be 1:1. Option D. You see, 1 mole zinc with the sulfuric acid, you get 1 mole hydrogen. 1 mole zinc with NaOH, you get 1 mole hydrogen. While the quantity of these are different. Sulfuric acid, it is 1 mole. NaOH, it is 2 mole. Suppose it is asking, what is the quantity of sulfuric acid and NaOH ratio? It will be 1:2, not in terms of mass, but in terms of moles. Here asked is the amount of hydrogen produced. It is 1:1, option D. Okay, next question. H2O2 reduces ozone. H2O2 reduces ozone. Ozone is a stronger oxidizing agent than H2O2. See, very simple logic regarding the oxidation characters of ozone and H2O2. You can easily understand. Assertion and reason are true, and reason is the correct explanation for assertion. In the karyam, ozone is a stronger oxidizing agent. There is no argument in that. Ozone is a stronger oxidizing agent, and it can oxidize H2O2. It will oxidize H2O2. So what is the point? See, this statement is well known to all. Quite obviously, what about the option A? H2O2 reduces ozone. That means ozone oxidizes H2O2. So O3 oxidizes H2O2. That means H2O2 reduces ozone. So both are true statements. And can we take it as correct explanation? Yes, also correct explanation. We will go for option A, no doubt about it. Both are true statements, and the reason is correct explanation for assertion. Standing explanation only. Okay, fine. Next. H2O2 restores white color of old paintings. See, this is another topic. Very important point. When we are making use of some oil paintings and all old paintings, on the course of time, it will become dull in color. Because in those paintings, we are using lead components. These lead components interact with the sulfur and forms lead sulfide. Lead sulfide is black in color, and over the course of time, the painting will become dull in color. What we do is, we do restoration. How to do the restoration? By washing with the H2O2. It is washed with H2O2, and H2O2 will oxidize the lead sulfide to lead sulfate. Lead sulfide is converted to lead sulfate. Option B is the correct answer. This is black in color and this is white in color. Lead sulfide, black in color, will be oxidized to lead sulfate, white in color, and thereby the paintings are restored. And the question is based on that, and the same reaction referred in the textbook also as an oxidizing reducing property of H2O2. Yes. Option B is the correct answer. Lead sulfide black converted to lead sulfate white. So what is the change in oxidation state? Sulfur -2 converted to sulfur +6. So N factor is 8. N factor is 8. Next. Per disulfuric acid. Per disulfuric acid means peroxo disulfuric acid. Peroxo disulfuric acid is option C. This is peroxo disulfuric acid. So 1 with the C, 1 with the C, straight away you get your answer. 1 with the C, straight away you get your answer. If you know what is peroxo disulfuric acid, you get your answer. Right? Baki check kiyam. 2A, is it correct? Perchromic acid. Yes, this is called perchromic acid. Then 3E, peroxo monosulfuric acid. This is peroxo monosulfuric acid. 2 mole condensing, you get this. Perhydrol, 4B, perhydrol. Yes, 30% H2O2 called perhydrol. 100 volume H2O2. Hyzon is H3. Hyzon is H3, like ozone, hyzon. H3. H3. Okay. Yes. Next. 30% solution H2O2 marketed as 100 volume. Already commented. Already discussed the point. Industrial preparation of H2O2 involves auto-oxidation of, it is referred in the textbook, option B, 2-alkyl anthraquinol. 2-alkyl anthraquinol, air oxidation converted to 2-ethyl anthraquinone plus hydrogen peroxide. And that is reduced back to 2-alkyl anthraquinol back by using hydrogen palladium. That's a continuous process. See, this is what happening. This 2-ethyl anthraquinol oxidized to get anthraquinone, and you get hydrogen peroxide, and you are removing this. And now this will be reduced back by using hydrogen palladium to this, and again oxidized, reduced, oxidized, reduced, oxidized, reduced, oxidized, reduced. Each time you are getting H2O2, and that can be removed. You are getting 1% H2O2, only 1%. That is further concentrated by careful distillation under low pressure, vacuum distillation, step by step. And final trace amount of water are removed by crystallization, freezing. Next. Again matching. Covalent hydride. Covalent hydride. Covalent hydride. Ammonia is covalent. Silicon hydride is covalent. See, except this, all are covalent. Saline hydride. 2 will be E. So only one choice. Saline hydride, only one, calcium hydride. 2 with the E, you get your answer. The others can have multiple combination. 1B, is it acceptable? 1B, covalent hydride. Yes, ammonia is covalent hydride. At the same time, it is electron rich also. Next, 2E verified. 3D, electron rich hydride. Yes, water molecule is electron rich. Ammonia also electron rich. Then 4C, electron precise. Silicon hydride, it is electron precise. Group 14 hydrides are electron precise. Then 5A, electron deficient. 5A, aluminum hydride is electron deficient. Group 13 hydrides are electron deficient. Group 14 hydrides are electron precise. Group 15, 16, 17 are electron rich. So, the other choices can have other combination also, but second one, only one combination, and by looking at that, you are able to confirm your answer straight away. Group 1, Group 2 hydrides are saline hydrides, ionic hydrides, salt-like hydrides, and they are real hydrides, because there we have H minus. H minus is available there. The real hydrides are them. Next. Hydride gap. All of you learned hydride gap. All elements in the periodic table gives you hydrides, except, see, keep noble gases away. I'm talking other groups. All groups are giving hydrides except 3 groups. Group 7, Group 8, Group 9. Group 7, 8, 9 are not giving hydrides, and they are called hydride gap. Group 7, 8, 9 are called hydrides, and they are called hydride gap. And even group 6 might have been included, but among group 6, one is giving hydride, that is chromium. Okay? And that's why 6 is not included. 7, 8, 9. 6 also might have come. In 6 also, it would have included, but it is not included because one among 6 group, one element in the 6 group gives hydrides, chromium, others not. Okay. Next. Water has higher boiling point than HF. Exactly. Assertion is true. The hydrogen bond between HF molecules are weaker than that between water. That is false. Assertion is correct. Reason is false. It will go for option C. See, in water molecules, the extent of hydrogen bonding is greater. Of course, in HF, hydrogen bonding is stronger. When you compare the hydrogen bonding, say in case of HF, this is HF and you are comparing hydrogen bonding. This is H2O, you are comparing hydrogen bonding. This is nitrogen, you are comparing hydrogen bonding. So when you compare the hydrogen bonding here, these are the three scenarios giving hydrogen bonding. These are the three examples giving hydrogen bonding. 1, 2, 3. When you compare the three hydrogen bonding, no doubt this is the strongest one, because fluorine is the most electronegative element in the periodic table, and therefore that hydrogen bonding will be stronger. But the extent of hydrogen bonding is greater in water, because in water molecule, you see in HF it is happening like this. HF it is happening like this, whereas in water molecule, the hydrogen bonding, all of you know, it may happen over there, it may happen over there. There are two lone pairs. It can happen over here, it can happen over here. There are 4 molecules surrounding one water molecule which are hydrogen bonded. So the extent of hydrogen bonding greater in water. The strength of hydrogen bonding, however, is greater in HF. Hope you understand the difference. And boiling point is influenced by extent of hydrogen bonding. So the boiling point of water is greater than HF because of greater extent of hydrogen bonding. Okay. So we will go for assertion correct, reason wrong. Option C. Option C. Volume strength of 1.5 normal H2O2. Another point all of you should remember. Molarity is equal to volume strength divided by 11.2. Normality is equal to volume strength divided by 5.6. Assuming old STP standards, 22.4 liters. New STP standard, it will be 22.7. Then it will be 11.35. Small variation. Anyway, so this is what we are applying. Normality given 1.5. What is the volume strength? So this is equal to 1.5. So what is volume strength? Volume strength is equal to 1.5 into 5.6. Option D. Option D, 8.4. 1.5 into 5.6. Option D, 8.4. Okay. And if you are talking about molarity, it will be some 4.2, half of that. You see, molarity and normality. Normality will be 2 times that of molarity, because it is a dibasic character. Okay, next. Hundred centimeter cube of a sample of H2O2 gives 1000 centimeter cube of oxygen at STP. The sample is said to be. You see, 100 ml, 100 centimeter cube means 100 ml. 100 ml give 1000 ml oxygen. So 1 ml gives 100 ml H2O2 gives 1000 ml oxygen. Therefore, 1 ml H2O2 gives 10 ml oxygen. It is 10 volume. 10 volume. Option C. Option C, 10 volume. 100 cc gives 100 centimeter cube H2O2 produces 1000 centimeter cube ozone. Sorry, not oxygen. Oxygen. Therefore, 1 centimeter cube H2O2 will produce how much oxygen? That is called volume strength. That is called volume strength. It is 10 volume, 10 volume. And 100 volume 30 percentage, 10 volume 3 percentage, 100 volume 30 percentage, 10 volume 3 percentage. So the answer is option C. Barium chloride dihydrate, the water molecules are interstitial. There are coordinated water molecules. See, water of crystallization referred in the textbook. Go through that. Coordinated water molecule, interstitial water molecule, and hydrogen bonded water molecule. In complex molecules, it is coordinated bond. In example given in the textbook itself, it is barium chloride dihydrate. It is interstitial. While if you take copper sulfate molecule, out of 5 water molecule, 4 are coordinated and 1 is hydrogen bonded. Refer text. When H2O2 treated with acidified potassium dichromate in ether medium, the ether layer turned blue. This is due to the formation of perchromic acid. The blue layer formed is nothing but perchromic acid, CrO5. And this is what the reaction. Dichromate interacting with H2O2, you get blue chromic peroxide or perchromic acid. And the structure of which also I am sure you remember the importance of this structure. Something like a butterfly structure, hope you remember, taught in the classes. This is what the structural entity of perchromic acid, and the oxidation state also. Oxidation state -1, -1, -1, -1, -2, -2, -3, -4, -6, -6. Sorry, -2, -3, -4, -5, -6. So this will be +6. That will be +6. Okay? Fine. Next. The dihedral angle of H2O2 molecule in the gas phase and the solid phase. See, you have to go through the molecular dimensions of H2O2 given in the gaseous state and the solid state. Please go through that. As I told earlier, open book structure. The dihedral angle, HOO bond angle, OO bond length, HO bond length in solid phase, gaseous phase. You have to go through that molecular dimension. And the question is based on that. Dihedral angle of gaseous phase, solid phase. Option A. Option A. It's a factual point. You need to study the molecular dimensions. Option A. 111.5 degree and 90.2 slightly decreasing in the solid phase. Next. Total number of water molecules that can be formed from the 3 isotope of hydrogen and the 3 isotope of oxygen. You see that it can be HOH, it can be HOD, it can be HOT, it can be DOD. Isn't it? It can be DOT. It can be TOT. See, such molecules exist or not? That is not the point. Hypothetically even, how many are possible? That is a question. H1, H2, H3. That is protium, deuterium, tritium. H1, H2, H3 is protium, deuterium, and tritium. All of you know. Now, taking those 3 isotopes and taking oxygen isotope 16. Oxygen isotope 16 I am taking, I am getting 6 combinations. Protium HOH1, protium deuterium, protium tritium, deuterium deuterium, deuterium tritium, tritium tritium. I'm getting 6 combinations. With the 1 isotope of oxygen. So with the 3 isotope of oxygen, it will be 6 into 3, 18 combinations. Answer will be option D, 18. I will get 18 combination. It's simply mathematical combinations only. With the 1 oxygen, you are getting 6 combination. With 1 oxygen, you are getting 6 combination. So, with the 3 different oxygen, you will be getting 18 combinations. Okay, fine. Next, the order of acidity of carbon dioxide, H2O, H2O2. CO2 is most acidic, anhydride of carbonic acid. CO2 with water we are getting carbonic acid. Okay, so CO2 maximum, and the second position will be H2O2, and option C is the correct answer. CO2 maximum, then H2O2, and then H2. That is the order. Understand? H2O2 is more acidic than H2O. Next, H2O2 will give you litmus test. H2O not. It's amphoteric. When hydrolith treated with water, it yields. What is hydrolith? What is hydrolith? Hydrolith is calcium hydride. Calcium hydride, when treated with water, you will get vigorous reaction giving calcium hydroxide, liberating hydrogen gas. Option D. Option D. You will get hydrogen gas. That probably is the method adopted for transporting hydrogen. The transportation of hydrogen in the elementary form is protected by law. Economically, it is not viable and it is not possible. So it is transported in the form of solid calcium hydride, saline hydride, packed with a perforated, asbestos sheet. At the point of destination, upon hydrolysis, you can get hydrogen gas released. And this compound is called hydrolith. This is called hydrolith. Okay, next. And that is what the reaction. The T half of tritium. Once again, referred in the textbook, all of you know, 12.33 years. The half-life of tritium. Half-life means, what is half-life? The amount of a substance, the time taken for the amount of a substance to convert to 50%. That is called half-life. The time taken for 50% conversion of the matter. That is called a half-life. The half-life of tritium is 12.33 years, referred in the textbook. Please, I'm sure you might have seen that. Option B. That was the last question from the chapter. There we conclude the discussion of some beautiful questions from the chapter hydrogen. So we will meet with another chapter in another class. Okay, take care. Bye. See you.